Hello, in this video, I'm going to show you an example of a Lambda calculus implementation within COQ. So we first start by defining our syntax, by defining variables, lambdas, which we also call abstractions, and function applications. And as a reminder, we are going to look at how variable is defined. We are defining it as a string. So from that, we know that an expression that is a variable is just the name of that variable. A lambda takes a variable name and the body of that lambda. And then finally, a function application takes two sub-expressions. And we are going to define our own syntax here to allow us to do operations. So we'll start by defining this substitution operator. I'm going to skip this definition for this video, but you can pause and try to figure out what's happening here. We define lambdas to be our own values. And then for our operational semantics, we define three constructors because in our small step semantics, as you may have seen in the slides, we have three rules. So since we are inside COQ, we can use COQ as our meta language. And this gives us the ability to say, hey, for this variable ID, we are going to define this variable to stand in X for the AST for lambda x.x. And then if we go ahead and print this, what we are going to see is this expression. And if we were to turn off the notations for a second and print this again, we can see that ID is an abstraction whose first argument is X and its body is also X. So let's go ahead and turn the notations off. And the reason we made this design decision to use comma in place of dot, whereas in Lambda calculus, this would be a dot, was to keep COQ from being confused in our usage of dot. So this just means that within our language, whenever we want to have the idea of dot represented, we are just going to use a comma. So let's go ahead and prove our first program. So here we are going to show that the program can step. So here we have the identity function applied to this thing. And we want to show that the identity function steps to itself. So just to get an idea of what's happening. So this thing here has a free variable in it. And in the future, we're going to discuss why we are not going to allow that. Just unfold ID. So here, we're going to go ahead and turn the notations back on. And then here, we see the AST of the program, but we can also turn off the notations. And this is very similar to an example of recursion that you could see. So we just have identity, and then we're applying it to Y and Z. And usually when you're writing Lambda calculus, you don't have this @ sign here, but we had to add this notation to make COQ comprehend our program. And I would like you to take a moment and pause here and try to guess which small step semantics rule or constructor we are applying here to apply this to apply identity to this and then step. So because we have a function application on the left, and on the right-hand side, we also have a lambda, as you're seeing. This is obviously the third rule from the slides that you're going to apply here. And then looking at the rules, when we print the definition of stepping, the core staff has made a decision to put the third rule first so that COQ would look for it first. And the reason for this is that the constructor tactic applies constructors to whatever we pass into it in the order that is given to it. And because the third rule is our most restrictive rule, due to it putting the most number of requirements on our arguments, it is also the most likely constructor to fail. And so it's a reasonable choice to try to apply it first, because it would allow us to see whether the entire thing is going to work or not faster. And here's an example of COQ getting smart on us. When we apply step beta, we would expect to get 2 goals. However, when we do that, COQ directly goes to giving us the value that we are going to get. And if you see, the rule down here is asking us to show argument in the parameter for the body of our expression is equal to our goal. So COQ is not asking us to prove this. And the reason for that is that COQ is, in this case, smart enough to figure this out on its own. So as an example, let us just go ahead and do this computation here. We are going to say subst of x and the lambda of yz in the body of x. And now that we have computed this, we can see that COQ, just by computing this substitution, that the answer was lambda y.z. So if we were to use step beta on a given goal that didn't even mention this substitution function, COQ just will think to itself, well, even though this didn't mention substitution, why don't we just run substitution here? Which is what is actually in our goal here. Another example of this is if you have a goal which is n plus 0 equals n, COQ would just prove that using reflexivity. And even though that's 0 in the program would make the 2 sides of the equation different, reflexivity is still able to prove that. So now, since COQ is happy with what we are doing, and all we have to prove is that this precondition, which is the argument lambda y.z, is a value. So let's quickly remind ourselves what the definition of value was. And going back to the class material, what was taught by the instructors was that values are a subset of the expressions and are those expressions that are also lambdas. And the way to implement that in COQ is by defining a predicate on expressions, which we call value, which also means that this expression here is a value. And this is only provable by a single constructor, which require the value to also be a lambda. And then since this expression just so happens to be a lambda, we can just apply that constructor, and that finishes our proof. This was one of the many ways to prove that this program up here takes a step. And now let's look at another way to do this. And allow me to turn the notations back on. So one way to prove this is to use the constructor tactic. Remember, what we basically did up here was to go find the constructor name and apply it. So when we apply the constructor tactic, it just finds the constructor for us. And then for the second one, we also had to apply the constructor, and that finished the proof. But if you wanted to make this even shorter, what we can do is just say repeat constructor until you can't. And that would just take care of the entire proof for us. So let's really quickly look at another program. Let's look at these 2 definitions. So the names are pretty suggestive here. So let's now consider this program here. We have lambda x dot x, and then we apply it to f, and then we apply that to the identity function, and we say that that step starts to f. So we are making the claim that this will always return f. And let's take a moment and think of this in terms of the constructors for transitive reflexive closures. I'm just printing their definitions here. The first one says a case where you're done, where you can step from anywhere to yourself, basically. And then you also have TRC front, where you can take one step, some other number of steps, and then end up where you wanted to. So I can just use the repeat constructors to make this work. But we can use eApply, because with TRC front, we used to use eApply to make a step instead towards proving our program. And then we can just say, just repeatedly use the constructor. And it figures out that when we want to prove a step about a concrete program, then repeat constructor can act as an automatic interpreter for our program. So here, after taking one step up here, we got to this situation where we called this function over here on the specific argument. And we are to use the result of that to do the substitution. So let us just simple first to get it to a form that's more easily understandable. And we immediately see that we have another function application, and we are not quite done here. So since we are not done, let's copy this again. And we take another step, and then repeat constructor. And now, when we simplify, we ended up here. And notice, this is exactly the definition of f. Lambda x applied to lambda y dot y. And since we are now at the bottom or at the end, and we can only step star to where we are, we can use apply TRC refl, and that finishes the. But this, as you may have noticed at the bottom of my screen, can even be shortened from what we had. Notice TRC front is a constructor. I'm going to down here. TRC refl is also a constructor. And COQ is smart enough to either not need this simple tactic or apply it when it needs to. So we could have just put in a bunch of repeat constructors and gotten our program to just work all the way through, except we have this problem here that also forced us to use eApply instead of apply. And the reason is this specific last intermediate step in TRC front is something that COQ can't quite figure out on its own. It's a little bit more tricky. And for that, we needed to use this eApply here. But if we transfer that idea to the repeat constructor and use repeat e-constructor instead, that can just do the proof all in one step for us. And notice this is possible because everything that constructor can do, e-constructor can do too, and then some more things. So that is why combining all these tactics into a bunch of e-constructors and then repeating them a finite amount of time simplifies this proof. And so these are the two examples I wanted to show you for this video.